Welcome everyone joining us online and here in the room for the next installment of our Sustainable Energy Seminar Series. If this is your first time joining us, my name is Scott Williams. I'm the Research and Education Coordinator at the Wisconsin Energy Institute. And the Sustainable Energy Seminar is something we do every other week in the fall and the spring to bring together lots of different researchers on campus and other experts who are focusing on sustainable energy challenges and solutions. Throughout the series, we'll hear from experts in engineering and science, as well as social sciences and humanities, to give a broader perspective and diverse perspectives on sustainable energy. This seminar is open to the public, but also for students in the Certificate in Engineering for Energy Sustainability, as well as the Master's in Sustainable Systems Engineering. And you can see we're in a hybrid format where we have some folks in the classroom here, but then also many of you are participating online. We do have live captioning as an option if you'd like to turn that on. You can click the show transcript button on the bottom of your screen. And it is being recorded for students in their class. If you do have questions, please use the Q&A. The chat may be disabled, but I should be able to see anything that you write in the Q&A. And I'll relay them to our guest speaker. And with that, I'll introduce today's speaker, Professor Chirag Gupta, who's an assistant professor in electrical and computer engineering. His work is really focused on semiconductor devices and wide bandgap semiconductor devices. So he's going to be talking about application for power conversion and really the opportunity for greater energy efficiency as we electrify a lot of our world, whether it's electric vehicles or heat pumps, as well as bringing in new cleaner energy sources to the grid.
Thanks, Scott, for the introduction. Hello, everyone, people online and in the room. I'm Chirag, and I'm going to be talking about, as the title of my talk says, energy efficiency and the importance of gallium nitride electronics in it. So energy efficiency is a pretty broad topic, and it's hard to just summarize or hard to explain it with just one small thing. So this is what I'm trying to do. I'm trying to speak about energy efficiency from the point of view of semiconductors, like how semiconductors can help improve energy efficiency and bring us to our ultimate goal of sustainability. So this is what I'm going to talk about. So about a little bit about myself. I'm Chirag. I'm an assistant professor in the electrical and computer engineering at UW-Madison. So before coming to UW-Madison, I was in India where I got my bachelor's degree in electrical engineering. After that, I came to United States for my graduate studies, where I stayed in this beautiful campus of UC Santa Barbara for about 5-6 years and got my PhD degree. And then, as all good things in life have to come to an end, then I moved out of Santa Barbara and went to Bay Area to get some real world industry experience, where I applied my knowledge of semiconductors to develop some products. And after going there, I realized that maybe academia gives me more flexibility in terms of making bigger impact and working on new and novel things. So as a result, I came to Wisconsin-Madison last year, and I've been working on things which are related to power electronics, energy efficiency, and semiconductors. So a combination of these things for the past year, and I will provide a glimpse of what my research is about and what I'm working towards on UW-Madison campus. And if you are interested in this, feel free to drop me an email. If you would like to learn more about this, don't feel shy. Please feel free to email me. I love to chat about what I do. All right, so let's get started. So this is a image of a US night sky taken by NASA, if I'm not mistaken, around 2010, 2012. When I saw this image for the first time, everyone has a different way of looking at things. But when I saw this, and I started wondering like how US night sky have changed over the years, because what it shows us is the amount of light that we are seeing from outer space. And basically, I came across this simulation study where actually people have done this work where they have simulated US night sky based on the information available from 1950s to 70s and 90s. And then 2025. And what you can see here is that as time has progressed, we as humans, we utilize more and more energy. And this is just one way in which we have used energy, basically, which is for lighting purposes. And there are so many more ways in which we use energy every day, but this gives us an idea as time is progressing, we are using more and more energy. So then I got a bit more curious and I started to look at how does the world uses energy. And then the better metric that I found was the amount of power that we consume is directly proportional to the GDP of the country, gross development product of the country. And here you can see there is a plot of GDP per person or per capita with power consumption. And you can almost see a linear relationship between them. Basically, the higher the GDP of the country, the more power they will consume. And so here is the visual linear line, and nothing wrong with that. I mean, we have more resources, so we end up using more energy one way or the other. But what is important here for us to note that the developed countries such as United States, United Kingdom, Japan, some other European countries, Australia, Germany, all are here, all are in this region at the top where they are using a lot of energy and their GDP is high. But what is going to happen is here, you see, they're the next in line countries, and then you have here Asian and African countries. So what is going to happen if we go back just one slide? What this plot has told us, as time progresses, we humans, we use more energy. And my concern or my thought is that what is going to happen when these countries in due course of time will start developing? They won't be underdeveloped or developing countries. They'll transition on to the next stage where their GDP will improve. So they will need more resources. And as you all know, we hear about all these kind of things where we are low on non-renewable resources, climate change is a problem, aren't we creating a big issue for ourselves? We all want to develop, but we eat up a lot of energy. And nothing wrong with that, but what we need to do is we need to create sustainable solutions for this sort of a trend. And basically what we need to do moving forward is, as these countries get richer, we need to provide same output by using less energy. We need to consume less energy to provide the same output. This is something that we should strive for. And when I pose something as general as this, the question comes to our mind is, have we done something like that before? Has it been done, or am I asking too much? So yes, we have done something like that before. And in this regard, science, technology, policy making, a lot of these different disciplines, they all need to come together and help us. And here I will give you a common example, which you might have used this morning. Average household refrigerator. What has happened is here you will see going from 1970s all the way to 2016. So what has happened is when the refrigerator first introduced, or not first introduced, but in this chart, you can see that the amount of energy it consumed was pretty high. And in course of time, with improvements, we have been able to drop the energy requirement by a factor of 4. And I'm sure none of you will complain about your refrigerator. At least they are performing at the same level when you were a kid. So at least during the course of my lifespan, I haven't complained about a refrigerator that, oh, it's not cooling properly or something like that. Things are getting more efficient. We are making the processes which are not efficient more efficient. We are figuring those things out. So this is something that we need to do continuously, and or at least that is one variable that is under our control. For example, if a process is 10% efficient and we make it, let's say, 80% efficient, it gives us room for 8 times more energy utilization. And that's what I mean when I say that we need to do this, where we need to provide more functional output by using less energy. And this is what my research or my motivation to do this work stems from, where to make things more efficient so that we are utilizing every bit of joule, every bit of energy. So now refrigerator is a not so cool example. So what are the cool examples where we would like these things? Well, your electric car, some of you might own it, some of you are thinking about it, but a lot of people, when I talk to them, the first thing they say, you know what, I don't like 250 miles limit on the electric cars. I would like my electric car to have 500 miles or 700 miles. I don't want to charge again and again. And I want my car to be cheaper. Everyone wants to, not everyone, but a lot of people want to buy a Tesla, but they can't afford one. So what do we want? Our wants are, we want more output by paying less. And when I say by paying less, it automatically translates into using less energy resources. Your dollar value is equivalent to the amount of energy or amount of resources that goes in building this car. So can we make Tesla provide 2x more miles from 250 miles to 500 miles at half the price? That's the goal. That's your refrigerator. Then power supplies, consumer power supplies. We use a lot of energy. No wonder people who are into gaming, they would know the value of this, or people who are mining cryptocurrency, they know the value of how important this is. Data centers, we all love using websites. We all love using tons and gazillions of storage. These data centers, with the amount of data that is being generated, it's getting stored somewhere. And basically to retrieve that data, to store that data, to manipulate that data, these data centers, they use a tremendous amount of energy. And you can imagine these data centers consume such a large amount of energy that some of these data centers are installed in countries where it's super cold, so that the cooling requirement, because of the inefficient power conversion, the tax that you pay is lowered. So moving forward with 5G, 6G, 7G, we are going to create a lot more data, and we need to process that data, and that processing of data is extremely important for multiple reasons, but the amount of energy it consumes, we need to improve that. And then this is another example of modern grid, where now we are slowly starting to move away from non-renewable sources. We are looking at renewable sources, at least for reasonable amount of time, where sun is quote unquote considered as a renewable source. So here you can use solar cells to convert the energy to drive appliances in our homes. So this is cool. And even for this, we would like to utilize the total amount of energy that our beloved solar cell has been able to convert. We don't want to waste anything. And as someone who likes saving, I hate the idea of wasting anything. My research is expensive enough. I don't want to waste anything. And that's the philosophy with which we semiconductor engineers are working towards. We want to make the power conversion or utilization of electricity as efficient as possible in all these systems to enable more productivity. So let's look at, when I started my work in this area, one of the key things that struck me was that we are surrounded by inefficient power conversion. We take X amount of energy and we don't produce X amount of output, one way or the other. So you can imagine how is power generated. If we talk about, let's say, solar power, it gets generated, but the way it gets generated, it's never utilized. So this problem can be simplified in one sentence, that the way we generate the power is not the way we use it. To give you one simple example is, your electricity gets generated somewhere, then it's get transmitted to your homes. Even in your homes, use the same lines for different purpose, for lighting, for your adapters, for your phones, maybe for your cars. So, and to run a lot of motors. So you can imagine that the same source is providing to different applications, and that requires some manipulation of power. And that manipulation of power is getting increasingly electrified. Basically, it passes through some type of electronics as time is progressing. And another way to think about that is you're driving, let's say, an electric car. It has a big battery. And that battery is doing everything. It's providing power to your stereo, to your steering wheel, to your mechanical assembly, if you have a display, if you have a computer, GPS, everything, it's providing the power. The source is the same, but the output is at different voltages, different currents. It needs different power. One application needs 100 watts, another application needs 1 watt. So how do you do that? How do you provide the power from same source? It needs to pass through some electronics to regulate that. And increasingly, what is happening is electric power that is finally getting utilized is now passing through more and more electronics. So if we go by US Department of Energy projections, in the last 25 years, we are almost increasing the total amount of electricity passing through electronics by 3x. And basically, if we want to look at the opportunity space in terms of dollars, it has almost $40 billion economic cost associated with it. And of course, needless to say, climate change and other societal needs are also associated with it. So why do we care? The reason we care is because these are the two simplest power converters which convert your energy from one form to another. Let's say you have a 12-volt battery, but you want only 1 volt of output. You use this circuit's buck converter. If you have 1 volt of battery, but you want 12 volt of output power, you use boost. So everything that we need more or less can be understood very simply with these circuits. And you don't need to understand these circuits, I barely do, but the simplest thing that you need to understand here is that it needs a switch. You can see the switch, I hope you can appreciate that. And these switches are essential for power conversion. Another way to simply understand it, if I want 1 volt from a 10 volt battery, I would keep my switch on for only 10% of the time so that effectively I get 1 volt. This is a very rudimentary way of explaining how this works. So this switch needs to be efficient. And basically, these are the biggest culprits of why our electronics is not efficient. Electronics, as we all know, is not 100% efficient. It incurs losses. And that's exactly what we are seeing here in inefficient transistor. So the solution to all this, not all this problem, but one part of this big puzzle is, can you make ultra efficient 99.999% efficient transistors? And that's what I'm aiming towards, that your power conversion everywhere needs to be extremely efficient. And for that, you need efficient transistors. So I'm going from a big system to circuits. And from circuits, I'm looking at this tiny, measly component, and I'm saying, you know what? I'm solving the big problems by making this small change. And this is truly a big deal because a transistor lies at the heart of everything. If you make an efficient transistor, it allows for efficient circuit. If you make an efficient circuit, it allows for building bigger blocks based on this transistor. So this is really, to be honest, at the heart of a power electronics system. So if you improve this, this allows for so many more things that we can't imagine just by looking at this. So we are going to go into details of what that is. So what is a transistor? Well, if you are aware of it, then great. But the simple way of looking at transistor is these are intelligent, compact, ultra-fast, but inefficient electrical switches. So this is the best switch in the world. It's almost 100% efficient. When it's on, it's on. It's like a metal. When it's off, it doesn't conduct anything. This is perfect. But what is the problem with that? It's almost a DC switch. The fastest I can do is how fast I can move my finger, on and off, on and off, on and off. The speed, they are extremely slow and not compact at all. So just to give you an idea, in your tiny electrical microprocessor chip that you have on your phones, on your laptops, They have only multi-billion electrical switches. So you can imagine this is no way. So what we need to do is we need to make these electronic components extremely efficient. So what do we need for an efficient transistor? So basically, we have to go to the basic definition of this. How does it behave when it's on? It behaves like a conductor. It behaves like a metal. Perfect switch. Low resistance, high current. Low resistance, high current. But when it's off, it behaves like an insulator. Basically, it can hold infinite voltage across it, which means very high breakdown voltage, very high breakdown voltage. So that's all we want from our transistor, to behave like an ideal mechanical switch or electrical switch, if you would want to call it that way. But what we also want from our switch is, we don't want those mechanical properties of being only able to work at slow frequencies or basically at few hertz. We want our transistor to be able to switch really fast switching times. So all in all, that's all we need from our transistor. And if we have that, we have transistor solutions which are extremely efficient. And of course, we have made those transistors which are extremely efficient, almost 99% efficient. So what do we want from those? Well, we want to use in those applications where they are inefficient. So we always strive to make advances at each and every level. Transistors, well, you made it efficient. Now I'm going to make my circuit more efficient. While I'm doing all this, well, this transistor, which was efficient for earlier circuit, for my advanced circuit, this is not efficient enough. And that's how the cycle goes. You make an invention right at the bottom of the food chain, and then the invention percolates, and then the feedback comes that you need to keep on improving. So this is something that we need from our transistor: low on resistance, high breakdown voltage. So we have simplified everything that a circuit designer or a system designer will come back and tell us. We'll say, we know what you want. You want an ideal behavior in the on state, like a metal, ideal behavior in the off state, and we are working on it. Low on resistance, high breakdown voltage. So this is something every power electronics engineer knows really well. Okay, so as I said, so what does this translate to? What does this mean? This mean for us is we want this on resistance, and resistance is what we learned in high school, rho L by A, where rho is resistivity. We want low resistivity. And breakdown field is directly related to critical electric field. Again, this is something we have all at least gotten this concept in our high schools. So what it turns out is that it finally translates to mobility and critical electric field, that the mobility of carriers in a semiconductor material and its electric field will give you an optimized performance of low on resistance and high breakdown voltage. So what are those materials? So here we have gallium nitride, silicon carbide, silicon. Some of you might have heard of silicon as the most common semiconductor, and which is true. Silicon is great, but recently what has happened is we want high breakdown voltage and we want low on resistance. So we ideally want to be in this corner. That's where we want to be. Silicon limit is here. We want to go here in this direction. So we need to use these new materials called silicon carbide, SiC, and gallium nitride, GaN. Okay, so these are the two new materials which are on the horizon. So this is one of the reasons why these materials, new materials, are more attractive for power conversion. And these materials are more commonly known as wide bandgap materials. So why is GaN great? Because it has wide bandgap. Basically, it can provide high critical electric field, which I highlighted here. This is what you need to be very high, and you need mobility to be pretty good. These are the two requirements which make for an efficient transistor. So GaN is great. It has wide bandgap and high mobility. So it satisfies the basic criteria. GaN is fast. It can switch from kilohertz to gigahertz. So it also satisfies our switch criteria that it's not a dud switch. It can work. And why this frequency is important, I'm gonna show here. So this is the circuit which we don't understand, right? But what we can understand is this is a switch, this is an inductor, this is a capacitor. The size of these inductors and capacitors are directly proportional to the frequency at which you use these transistors. So if a transistor can only work at kilohertz, these are going to be massive. But if the same transistor can switch up to gigahertz, the size of these passive components will be very small. So that's the difference between your laptop and your mobile phone. So just to give you an idea of the form factor, if you can switch faster, all the computing power or all the conversion can happen in small area. So that's why this is extremely important. GaN checks off this box as well. And finally, the most important thing about these two, it needs to be reliable and have a roadmap towards lower cost. And I cannot undersell this point, because no matter how good your electronics is, if it's too expensive, no one is gonna buy. Going back to the argument of why we don't see Teslas everywhere, because they are not cheap. Everyone wants to help the environment without paying extra money. And that's why you need to be reliable. You don't want your cars, you don't want your laptops, you don't want your things breaking down day in, day out. You want them to survive and needs to have a roadmap towards lower cost. As time progresses, we want to provide more functional output at less price. So this is what GaN has done. These are just some news headlines that I have added to just convince you that yes, it's possible. So what has happened is people have worked on GaN, and I was thinking of what is the best way to convince you that this is real, this is not fake. So I went to Amazon and I thought, okay, let me try to buy a GaN charger. So you can buy a GaN charger to charge your laptop as well as your phone. This is ultra fast, but you notice the price. GaN is still expensive. There is still work is needed to make it cheaper so that everyone owns a GaN charger. So this is a work in progress. So when I tear down this charger, what do I see? I see a bunch of things. Again, it's too complex for me to understand. So I just focus on this one part, which is the GaN power block. Okay, so what is this GaN power in this? And as I said before, this is at the heart of everything. So let's go to the heart. So gallium nitride transistors, they have been around for some time. They were invented in 1992. They were commercialized in 2015. Another point I want to put across, this isn't easy. It takes time. It takes time to mature. It's like wine. To become commercially available, to solve all the problems in the world and make it ready for customers, it's no easy task. This semiconductor technology takes time. So, and still, the price is high, we need to drop that. So this is what I'm looking into. So this is a lateral device. If you are familiar with semiconductor engineering, you might have heard of silicon MOSFETs. So where you have a source, drain, gate. So this is a transistor design. These are suitable for high voltage applications, 600 volt. And this is where the electrons flow from source to drain. So this is very similar. The concept is very similar to a conventional MOSFET. If you are aware of, if you are not, then I'll try my best here. So this is a transistor where you have this channel. So when this channel forms, this behaves like a metal. When this channel is not there, it behaves like an insulator, conductor versus insulator. But the problem in this design is you need space to hold the voltage. And that's what this design gave to this design. It's called laterally diffused MOSFET. So this is popular in silicon industry. And a lot of our devices that we use have this. But what happened, people thought, okay, let's try to do something better with GaN. They used the same idea, gate drain spacing. And they produced devices which were better than silicon. So now, if everything is done, what do I need to do? I need to drop the price of that charger so that all of you can buy it. And that's one of the key things that I'm interested in, to make my semiconductors more efficient, better than where they are, to make sure they are commercializing. So this is what I'm going to talk about next. So this is what we were talking about, right? 100-volt GaN, 100-volt silicon, okay? The performance of GaN is so much better. We want resistance to be smaller, and compared to silicon, we are 3 to 4 times smaller, which is great. We have made a better technology. But the problem is our GaN is 3 times more expensive compared to silicon. And that's why your charger, which should cost like close to $20, $30, it's costing you $60. This is not cool. No one likes it. And GaN is a new technology. So there is risk associated with it. You have never used GaN material before. You have used silicon. You like silicon. You love silicon. Okay, so I'm going to end up using this. And that's what the world chooses. Even if there is a better technology available, if it's not cheap, no one goes for it. And that's why you don't see GaN everywhere. It's a niche application. So, and the answer is not technical. The answer lies in economics. But since I have to be a professor here, I can't teach economics. I'm an electrical engineer. So I'm going to solve this problem in electrical engineering way. So let's do it. So what do I need to do? I looked at it closely and I figured that GaN actually can be 20 times better than silicon, but currently it's only 3 to 4 times better than silicon. So that's the technical problem. I need to make my gallium nitride way more efficient. And if I can reach even half of my goal 10 times, I can make a GaN charger 3 times cheaper than silicon. Then everyone will buy GaN chargers. And this is what I'm interested in doing. So let's see what the technical problem is. The technical problem is GaN can hold 300 to 350 volts in 1 micron. But in today's transistors or devices which are in the market, you can only hold 20 to 50 volts per micron. So we are very far from the true potential of GaN. We are barely scratching the surface for these materials. So what do we need to do? If we can go from 20 to 50 to around 100 to 150, still 3 times lower than the ideal limit, we'll be good. We'll improve our devices significantly. So what is the problem that is not allowing us to go from here to here? Is the presence of these surface traps. These surface traps causes reliability issues. And without going into detail, I'm going to say I have one solution. This is what I'm looking into, how to get rid of these. People have been trying for 20 years. No one has been successful in getting rid of these. So these are called surface traps. So what I'm going to do, I'm going to change the problem. This is what I'm proposing. Well, if smarter people than me weren't successful, how am I going to be successful? So I'll say, I'll avoid this problem by creating this design. So in this design, what I propose is, I make this material so thick, that they are super far from my channel, these red lines, and my gate metal is pretty close compared to this. And this idea can result in lower impact of these surface states. And basic idea is that this would allow us to achieve our goal of 100 to 150 volts per micron, basically 5x. Important. And this part of this demonstration has been done for high frequency devices where similar problem limited the performance, and with nitrogen polar or with this design, they were able to demonstrate high frequency performance. My goal is to use similar idea and develop 600 volt power transistors so that we can achieve this. And this results in higher performance transistors, which in turn reduces the cost and gives us this 10 times lower on resistance compared to cell. So this is one area that I'm very excited about and currently working on. As a semiconductor materials and devices guy, as I said, silicon is everywhere. We are looking at silicon carbide and GaN, but people are already asking this question, what's beyond GaN? In academia, we need to think of 20, 30 years beyond what's going to come. And the idea is that there are more materials which are on the horizon. So this is another area where I'm expanding my research into gallium oxide and diamond. Diamond, it's the same diamond that some of you might be wearing, but you can use it for electronics. And diamond has some special properties which make it one of the best semiconductors to use. And again, to remind you that this is the resistance, this is the breakdown voltage. We want to be here. So at some point, I won't be surprised that you will see diamond in your devices. And that diamond will definitely be different from the one that you are wearing. Your electronics will always go cheaper. They won't go that expensive. So this was one of the areas that I'm interested in. So solving current gallium nitride challenges, looking at new materials. So far what I have discussed are the challenges which are at the transistor level, which is where I started my conversation. Now I'm going to move on to the electronic section. So now I come back to this and I say, you know what, I'm working on this. What about all this other stuff? What are we going to do about this? And the idea is, well, there is a lot that we can do here. If we cannot do anything here, there is still a lot of work to be done. Can we make this all onto a same chip? Can we integrate some of these chips? Right now, this is a GaN chip and all these are silicon chips. Can we bring some of the functionality to gallium nitride? And the idea is, yes, we can. Why do we need that? Because we'll convert this from this big, bulky, ugly to this printed circuit board. And maybe someday all this into a chip because we want to reduce the form factor, size, everything, make it fast. And this is a natural progression of transistors where you take discrete devices and convert them to integrated circuits. So what do you need? We need a complementary transistor. We need P-type material, N-type material. This is the most common thing which undergraduates learn in electrical engineering. So to make integrated circuits, we need complementary transistor, N-type and P-type. Great. GaN has both. GaN has both N-type and P-type. So what's the problem? Well, we want comparable performance of these. So the problem is electrons are very good in GaN and holes are pretty bad in GaN. Here, heavy holes, they are 10 times worse in gallium nitride. So the conductivity is 10 times worse. You need to make devices 10 times bigger. Basically, that impedes the development of complementary devices. So what do we need? We need something which is comparable. We need holes which are comparable to electrons, and this is where we need to figure out how do we use these holes in our devices. Currently, we cannot. We can only use these heavy holes which are 10 times bigger than electrons, and we cannot use them. That's why we don't have gallium nitride integrated circuit. But if we can somehow magically use these holes called light holes, we can make gallium nitride integrated circuits. So how do we do that? So we take inspiration from silicon technology. In silicon, what have they done is they have used strain technology. They have pushed the material, quite literally, pushed the material by implanting a bigger atom close to a smaller atom. And this bigger atom pushes the material and it alters the effective mass of carriers. And this is the similar thing we are doing here. Basically, this was the band diagram before we use the strain, but you can see that even if you don't understand, you can appreciate that once you put down strain, this changes. And basically, this allows you to use light holes. And if we do the same thing in gallium nitride, we can get light holes, we can get P devices, we can make high performance gallium nitride integrated circuit. So this is what I'm also working on. How do we do that? We make it by engineering the device structures, by making fin geometries. So let me give you a little bit of where I am in my research. So Once I did all this stuff that I showed you, I was able to improve hole conductivity only by a factor of 2. What I need is, can I improve it by a factor of 10? This is what we are looking at, and this is a work in progress. Let me go back and show you. So it's 0.2, we are here. We want to go here because then these and these are comparable. Electrons and holes are comparable. N channel and P channel are comparable. Then we can make integrated circuits. So we are halfway there. We need to drop this by an order of magnitude, by 10 times. We have only done it by a factor of 2. So this is an active area that I'm working in to, sorry. So we still need to improve by a factor of 5. And of course, this is just one part of integration. There are so many ways in which we can integrate electronics to make it better thermally, for higher electrical performance. There are many ways in which we can achieve this behavior. So this is exactly what I'm interested in doing. So the long-term research goal is to take all this junk all on one chip so that it's nice, easier to understand, as well as is ultra efficient. And the ultimate goal is to keep working until the slopes comes down. And this is interesting to a lot of people. So that's the ultimate research goal, by working with people, with different types of engineers, mechanical engineers, circuit designers, systems folks. This will take a lot of effort to come here, and here I am providing my little bit to it. Thank you, everyone. And if you have any questions, please feel free to ask me.
As we wait for folks online to ask questions, maybe I'll start off, or if you want to ask a question.
Yeah, so you kind of talked about how expensive GaN is right now. And I guess I was just a little bit confused. Is it more so the workability of like mass production? It kind of seemed like with the risk differences, or is it more so the materials like obtaining the gallium and the nitrogen?
No, so it's a combination of everything, but the biggest thing is that the performance of GaN is not as good as high that it will warrant low cost. So let me put it this way. For example, the form factor of GaN is not small enough at the moment. The challenge is at the device level. So gallium nitride theoretically is supposed to outperform silicon by hundreds of times. Basically, if you have a silicon electronics, you will need this big of an area. But if you have GaN, you'll only need this big of area. And you can imagine so many applications where people will say, no, I want this small thing. I don't want the bulky thing, right? So, but what has happened is the advantage of this small thing doing the same thing as this big, you want the cost advantage as well. And that hasn't come through. The only reason is the device level challenges, the fundamental challenges, you can say, people haven't solved it, but they are already starting to commercialize. That shows the potential. So gallium nitride can be 100 times better than silicon, but we are only 3 times better than silicon, and that is good enough for commercialization in some space. So my point is, if you can solve the fundamental challenges and improve the performance, commercialization will take off. It's still at the transistor. It's at the semiconductor level, and it's a combination of multiple things: manufacturing challenges, processing challenges, design challenges,
right now,
reliability. Yeah, so it's
because that's not worth the cost yet to.
Exactly. It's not cheap enough, or the performance is not so much to offset the cost. Another way to put it is.
Maybe jumping off the question, are there any kind of long-term challenges in terms of sourcing the material, gallium, since silicon is much more abundant?
Right. People don't talk about it. Yes, you are absolutely right. Silicon is much more abundant, but the amount of gallium that we need is not as much. So let me put it that way, especially for power electronics applications, we use only 1/60th of silicon, or even lower than that. We use the gallium amount is negligible compared to what you use for silicon. So it balances itself out. That is a factor that doesn't affect the price so much. I wouldn't imagine, at least at this point. Maybe in like 1,000, 2,000 years when we are using so much of gallium nitride, then it might be a problem. But for now, people don't consider that. There are other big issues to do.
I would assume maybe there's military applications, or there's a lot of interest from the Department of Defense because of their special capabilities.
Exactly. The biggest reason why gallium nitride is here because of DoD support. For high frequency transistors, so Navy has been the biggest supporter of gallium nitride. They have sponsored gallium nitride research, and gallium nitride is useful in high frequency application, in radar application. So that is one of the bigger usage of that. Gallium nitride transistors can enable they are enabling 5G, and they will be the technology for 6G for high frequency applications. And there are other extreme applications that you are alluding to, high temperature, space, all that kind of stuff is also.
Or, just like I can't remember the amount, how much soldiers have to carry in their backpack, right? The amount of weight, it's like another person basically. Yeah. So I imagine having these efficient devices.
Exactly. So right now they are in a niche, but they have entered consumer market, which is a good thing. That slowly that will also translate into industrial funding, venture funding, basically more effort going into improving these devices, and we'll reap rewards of that. Just beyond government support.
We've got a question from Doug. Do nanotube forms of gallium nitride address any of the cost or performance issues?
So not at the moment. I think what you are saying is again, more fundamental research kind of question. I would say at this point, the simple answer to your question is no, but it's not a permanent no. That no depends on what kind of nanotubes, how do we make that? So it has to be a full argument. So it's something of a research idea that Doug is proposing, and I would say it needs to be validated. Yeah.
I know you've got to leave in a couple minutes. If you've got another question.
Yeah, I guess just to round out. So you kind of started off with talking about the GDP and everything. Do you see that plateauing sooner? I know you're not doing economics, but do you see that plateauing sooner rather than later because of new technologies, or do you think it'll just plateau almost more naturally rather than continue rising?
I think it's hard if I have to make a bet, I won't say it will ever plateau. My hope is that we will move on to sustainable resources or renewable resources before we plateau. So I think the conversation comes more into play from the fact that we are using resources which are going to end someday. But if we switch to resources, then I think we may be okay. But of course, we have to maintain climate change and all that kind of stuff, like how we do that. But it's a slow quasi-static process, and it's hard to imagine that we won't use more energy as time goes by. That's what history shows us, that we don't slow down. The only thing we can do is manage our output or byproducts better and use the cleanest form of energy that we can.
You've got
yeah. If there is any other question, I can take one more.
I don't see any online, but feel free to email me or Professor Gupta if you have any more questions online. But thank you so much for your presentation today.
Great, thank you.
We'll be back in 2 weeks with a presentation from Professor Ophelia Venturelli from biochemistry.